Let us try to derive expressions for work done in various types of thermodynamic processes. And we will also see in brief how do we represent these processes on a PV diagram. So to begin with, we have an isochoric process. Isochoric process is a process where the volume is kept constant. Since volume is constant, its change is zero. Obviously, derivative of constant is zero. Since dV is zero, we simply see that since work done is given as P dV and dV being zero, the work done is zero straight away. So, an isochoric process does not perform any mechanical work. On a PV diagram, it can be represented in the following manner. Suppose there is a state A and the system goes to state B by maintaining constant volume. So volume should not be changed. So whatever volume that is initially, say VA, is kept as it is. So one has to move vertically downwards or vertically upwards, depending upon whether the pressure is increasing or decreasing, B or B dash. So either way, an isochoric process, which is a process at constant volume, has to be represented by a vertical line on a PV diagram. And this can be readily seen that since work done is area under the curve on a PV diagram, we can readily see that area under this curve is 0. So this curve does not have any area lying under it. So obviously the work done is 0. So this is for the isochoric process. Similarly, for the isobaric process, which is the process at constant pressure. So since pressure is constant, its change is 0. And on the PV diagram, it will appear exactly opposite to the isochoric process. So we will have a horizontal line. Since pressure is kept constant at a typical given value, and volume is allowed to change from say some initial volume V1 to final volume V2. So isochoric process appears on a PV diagram as a horizontal line. And again, now since dW is PdV, if we integrate this dW to find out the total work done during this process, what we get is integral PdV. Since pressure is constant in this process, isobaric, it comes outside the integration, and integral dV from V1 to V2, of course, there are lower and upper limits, is V. Integral of dV is V from lower limit V1 to upper limit V2. So this W is nothing but P into V2 minus V1. So this is the expression for work done during an isobaric process. We can also define another thermodynamic quantity with the help of this expression. We know that PV is just nRT. So P into V2 is nRT2 and P into V1 is nRT1. So we get this W, in fact this is the delta W, the work done, net work done, as instead of PV2 we write this expression, and instead of PV1 we write this expression. So nRT2 minus nRT1. And we note here that Q dQ is du plus dW, right? So dQ is the change in heat, Q2 minus Q1. Du is the change in internal energy, U2 minus U1. plus dw is the work done, which is this much in this case, nr t2 minus nr t1. So this is simply the change in head q, which is u2 minus u1 plus pv2 minus pv1, or we can see that this is u2 plus pv2 minus u1 plus pv1. This is q. So anyway, we can call it as delta q, changing it. This quantity is defined as enthalpy. So let us call it as H2. This entire quantity is enthalpy H, defined as U plus PV. And this quantity is just H1. So delta Q in this case is just the subtraction of enthalpies of state 2 and state 1 respectively. We note that enthalpy is defined as U plus PV, and all of these quantities are properties of state. So they are state functions. U, P and V are state functions. So obviously enthalpy is also a state function and not a path function. This is an important point to note. Let us continue our discussion further for work done in an isothermal process. In isothermal process, we see that temperature is constant. That also means that internal energy is constant, because internal energy is related to kinetic energy and hence the temperature of the system. At least in the case of ideal gas, it is directly connected to temperature. So since U is constant, du is 0. And we see that from the first law, dq is du plus dw. So since du is 0, dq is equal to dw. This is what we have for the isothermal process. Now, as far as work done is concerned, let us just rewrite this formula. dw is equal to pdv, and we know that pv is equal to nRT. This means P is equal to nRT by V. So dW is equal to nRT by V into dV. So we have substituted for P by this expression. If we integrate this, integral dW, which is the work done, so integral nRT by V dV. Now note that n and r are constants anyway, so they are taken outside the integral. And if the process is isothermal, temperature itself is also a constant. So it is again coming outside the integration, and we are left with integral 1 by V dV. And we know that this integral is just log V. Of course, this is a process, so volume must change from some initial value V1 to final value V2. So this is from V1 to V2. So the limits appear here as V1 and V2. So we write it as upper limit minus lower limit, and log of a minus b is just log a by b. So we have nRT log of v2 by v1. So this is the expression for work done for an isothermal process. We also see here that PV is nRT, and if T is constant, N and R are constants, so this entire thing on the right hand side is constant. So for an ideal gas isothermal process, P is product of P and V is constant. This also means that P is inversely proportional to V. So on a pressure versus volume diagram, it appears as this type of curve showing inverse proportion. So as P decreases, V increases, and vice versa. Instead of V, if we are supposed to use P, we see again here that P is inversely proportional to V. So V2 by V1 has to be P1 by P2. That's what this inverse proportion means. So instead of V, if we write the same formula using the variable pressure, we get it as log of P1 by P2. Note that P1 is the initial pressure, P2 is the final pressure. And V1 is the initial volume, V2 is the final volume. So this is the expression for work done in an adiabatic process. Sorry, the isothermal process. So let us now try to derive the same for adiabatic process. For adiabatic process, we have already derived that PV raised to gamma is a constant. Let us call it as K. So P is K by V raised to gamma. This we are going to use in our discussion because work done is integral dW. This we have now become familiar with as integral P dV. So instead of P, write it as K by V raised to gamma dV. K comes outside being constant. Integral V raised to minus gamma dV. Right? So we know that integral x raised to n dx is x raised to n plus 1 divided by n plus 1. Right? So this gives us k into V raised to minus gamma plus 1 upon minus gamma plus 1. So this is equal to k V raised to, of course there are limits again from V1 to V2. So let us put the limits from V1 to V2. So this gives us k upon this minus gamma plus 1 is same as 1 minus gamma, and limits V raised to 1 minus gamma from V1 to V2. So this is just equal to k upon 1 minus gamma V2 raised to 1 minus gamma minus V1 raised to 1 minus gamma. So anyway, we have derived the relation, but let us just try to simplify it further. This can be written as k upon 1 minus gamma into V2 upon V2 raised to gamma minus V1 upon V1 raised to gamma. This V2 raised to minus gamma is nothing but 1 upon V raised to gamma, right? Okay. Now here, let us try to simplify this. Since we know that PV raised to gamma is constant for an adiabatic process, we see that P1 V1 raised to gamma is equal to P2 V2 raised to gamma is equal to that constant K appearing here. So this also means that K by V1 raised to gamma is equal to P1 and K by V2 raised to gamma is equal to P2. So just look at this equation. This K appears here as well and here as well if we put it inside these square brackets. So this is just 1 upon 1 minus gamma V2 into K by V2 raised to gamma minus V1 into K by V1 raised to gamma. So let us use these relations to get 1 upon 1 minus gamma V2 into P2 minus V1 into P1. Again, we note that PV is just nRT. So this is P1 V1 being equal to nRT1 and P2 V2 being equal to nRT2. This gives us 1 upon 1 minus gamma into nRT2 minus nRT1 equal to nR upon 1 minus gamma T2 minus T1. Now we should note that gamma, which is the ratio of Cp by Cv, is typically greater than 1. So this subtraction in fact is going to be negative. So to adjust this, we will write it as nr gamma minus 1. So I multiplied this by minus 1. Similarly, multiply this by minus 1 to get T1 minus T2. So this is an expression for work done during an adiabatic process. Now we should note that for isothermal process, we have PV is equal to constant and it gives us P proportional to 1 by V. And for an adiabatic process, PV raised to gamma is a constant So P is proportional to 1 by V raised to gamma. So this is just 1 upon V raised to 1, and this is just 1 upon V raised to say 1.3 or 1.4, since we have seen that gamma is larger than 1. So both of them are showing inverse proportion, but this falls at a much higher rate. So if we compare these two processes on a PV diagram, both of them are going to fall as a rule of inverse proportion, but the one which falls at a rapid rate is going to be adiabatic, whereas the one which falls at a lower rate compared to the other one is isothermal. If we recall the other two processes in the same diagram, the line which is horizontal is going to be isobaric at constant pressure, and line which is vertical is going to be isochoric, that is constant volume process. Thank you.